Everybody, the people in the room, of course, as people online. We have the pleasure to have here Ilaria Ruffa. This is just, I'll leave in a few seconds the word to Enrica for the introduction. So, as usual, at the end of the talk, we will give you the word in case of questions. So, see you later. Enjoy the talk. So, please, Enrica.
Yes, thanks, Crescenzo. Good morning. It's a pleasure for us to have Ilaria Ruffa visiting us this week. With Ilaria, we started our collaboration a couple of years ago, since inside our Vegas survey, we start having a optical follow-up of the H1 radio sources. And Ilaria got her PhD in astrophysics in 2019 at the University of Bologna. Then she moved in Athens for University of Athens for a postdoc. And now she is a postdoc at Cardiff University. And yeah, she will present her work on CO dynamical modeling.
Good morning, everyone. Thank you, Enrica, for the presentation, and many thanks for hosting me here these days. Many thanks to you and Marilena, of course. Today I'm going to talk about the Wisdom project, which is co-led by Tim Davis in Cardiff and Martin Bureau in Oxford, and carried out in collaboration with all the beautiful people listed here and many others. But before jumping into the details of the Wisdom project and some of the results we obtained so far, let me introduce the concept of supermassive black hole host galaxy coevolution. So, the observational efforts carried out over the past 3 decades demonstrated that the mass of supermassive black holes found at the center of galaxies correlates with a number of host galaxy properties, suggesting a sort of self-regulated coevolution between supermassive black holes and host galaxies. Now, the correlation between the black hole mass and the central stellar velocity dispersion has been initially found to be the tightest. And here I show the plot, the first M sigma plot from the seminal work of Merarese and Merritt 2000. Over time, however, as the number of supermassive black hole masses increased, evidence for divergence between different galaxies, morphologies, and masses have been observed. And here I show 2 examples from the works of McConnell-Emma and Van der Bosch 2016. In particular, if we focus on the work of McConnell-Emma 2013, they found that the best fitting M sigma relation is different for early and late type galaxies, here indicated, plotted in red and blue colors, respectively. Now, the origin of these correlations is not yet clear, but it is a popular idea that aging, fueling, and feedback processes can play a crucial role in setting up this self-regulated coevolution. And the reason why this is happening is very well explained in this cartoon from Harrison 2017, in which we can see that the galactic gas reservoirs on kiloparsec scales can be used for fueling both the AGN and the star formation activity. But let's focus on the left-hand side of the plot for a moment. So if the gas on galactic scales loses sufficient angular momentum to reach the inner parsec scales, it can be used for feeding the central pre-existing supermassive black hole. While this black hole grows in mass, at some point it switches on and starts to release a huge amount of energy onto the surroundings via winds, jets, outflows, which can have an impact not only on the usable fuel for the aging activity, but also on that used for the star formation, in the galaxy. And therefore, probably having an impact also in the correlations that we observe. The many details of these processes, however, are very poorly understood, and therefore, the take-home message here is that the supermassive black hole host galaxy connection is still hotly debated. Now, a crucial point to try to understand better what's going on between supermassive black hole and host galaxies is to gather as much as possible high-precision supermassive black hole mass measurements. The most reliable methods adopted so far, well, no, the most reliable methods at all consist in getting supermassive black hole mass measurements consist on dynamical studies of matter orbiting within the black hole sphere of influence. Now, the methods adopted so far basically consisted on studies of stellar, ionized gas, and matter kinematics. Each of these methods, however, has unavoidable limitations, pros and cons, and I'm going to explain why in a moment. For instance, studies of stellar kinematics are usually challenged by dust extinction. They require also a very high resolution, which is so far was difficult to achieve in optical studies in most of the cases. And this is also typically restricted to axisymmetric objects, which means that this kind of studies are typically biased towards early type galaxies. Studies of ionized gas kinematics, on the other hand, are typically challenged by non-gravitational forces within the gas or turbulent gas motions superimposed on circular motions. So, making hard obtaining accurate supermassive black hole masses in this kind of studies. About matter kinematics, so typically these kind of studies allow to obtain very high precision measurements, mainly because masses usually trace material that is very close to the supermassive black hole. The problem in this case is that masses are usually observed only in a certain type of galaxies, in particular Seyferts, and they are detectable only in edge-on disks. So I hope I managed to explain why these methods sometimes are difficult to apply. For this reason, it was clear since the beginning that an alternative robust tracer for supermassive black hole mass measurements in galaxies of different types was needed. And in the past decade, thanks to the resolution and sensitivity provided by the latest generation of submillimeter telescopes such as ALMA and ALMA, for instance, a new technique has been developed and already successfully applied to a wide range of objects. And this technique consists on probing the molecular gas kinematics within the radius of the supermassive black hole sphere of influence using CO, mostly CO emission lines. So let me explain how this technique works in few words. Basically, what we want to do is to obtain high resolution CO data, with the resolution in particular allowing us to resolve the radius of the sphere of influence defined in that way, typically, as indicated on the left-hand side. And here I show a beautiful example from North 2019 of the radio galaxy NCC 383, in which they detected this beautiful CO disk with a spatial resolution of the order of 50 parsec, well resolving the radius of the sphere of influence. And we can see that from the plot on the right-hand side, which is basically the position, the measure axis position velocity diagram of the gas velocity curve, in which we can clearly distinguish a circular velocity component here indicated by the red dashed line, plus a symmetric velocity increase at the center, tracing the Keplerian motion of gas orbiting within the sphere of influence of the supermassive black hole. And the goal in this kind of techniques, the primary goal, is to detect indeed this Keplerian motion at the center, which through dynamical study that I'm going to illustrate in a moment, allows us to estimate the supermassive black hole mass. Now, the studies, CO dynamical studies, using CO as a tracer for estimating supermassive black hole masses has many advantages. First of all, CO is an ideal kinematic tracer because it's typically dynamically cold, is relatively bright, and unaffected by dust extinction. It also typically allows to obtain supermassive black hole mass with uncertainties that are of the order of 1.2, 2 times smaller than any other technique, that the techniques that I illustrated a moment ago. This is also the other huge advantage, is that this technique is also enforceable to all types of galaxies, from late to early type, active, inactive, any type of galaxy. And also, it allows to obtain black hole mass measurements that are typically independent. Of course, they are independent of the stellar and ionized gas kinematics, and therefore is useful for cross-check studies between different techniques. And here it comes the WISDOM project. So WISDOM stands for Millimeter Wave Interferometric Survey of Dark Object Masses, and has the primary aim of measuring supermassive black hole masses using very high resolution CO observations from ALMA and CARMA. Here I provided the link to our website if you want to have a look and want to know more about the team, the project, and the papers published so far. So the WISDOM project, the WISDOM sample consists on 35 nearby galaxies, which has been selected. So the only selection criteria was to be able to resolve the radius of the supermassive black hole sphere of influence. And for this reason, these 35 galaxies listed here in this table include different types of galaxies. And this is, I think this is a strength of the sample. Now, thanks to the data set that available to the WISDOM team, we already carried out obtained high precision supermassive black hole mass measurements in 6 typical early type galaxies, a peculiar luminous infrared galaxies, and also a dwarf early type galaxy. But the quality, the high quality of the data available to the WISDOM team allowed us to carry out also a lot of additional science. And here I provide some examples. For instance, we investigated the scaling relation between supermassive black hole masses and CO lines, the properties of giant molecular clouds in nearby galaxies, and so on, so on. But in the second part of my talk, I'm going to illustrate some of the latest results obtained for these 2 galaxies, 1574 and 4261, that are going to be hopefully published in this paper that we submitted a few days ago. So let me start with 1574. This is a part lenticular galaxies very nearby. part of the Dorado group. Observations at various wavelengths suggested that there is no nuclear activity in these galaxies, and in particular, there were no previous supermassive black hole mass measurement. And here I show an optical map of the target from the CGS survey. ALMA data in ALMA CO2-1 data in 3 different array configurations were available and combined for this study, achieving a final spatial resolution of 14 parsec in this case. And as you can see here, we detect a beautiful CO2-1 disk. In this plot, I show on the top left the moment zero or integrated intensity map. On the top right, the mean line of sight velocity map. Bottom left, the mean velocity dispersion, and bottom right, the measure axis position velocity diagram or velocity curve. So, as you can see, we detected a nice, a beautiful CO2-1 disk extending like 200 for 200 parsec, about 200 parsec at the center of the galaxy. The bulk of the gas, as we can see from the moment 1, is regularly rotating, even though we observe some kind of distortions in the isovelocity, that kind of S-shaped distortions in the isovelocity contours that may indicate the presence of both, they can be indicative of both warps or non-circular motions, this kind of features. But if we look at the measure axis BVD, we can clearly see that there is a circular velocity component at the center, a mild velocity increase, which may be indeed related to motions, gas motions under the gravitational influence of a central supermassive black hole. We carried out the kinematic modeling of this gas using KineMES. KineMES is a tool from Davis et al. 2013, adopting a forward modeling approach consisting on input guesses for the gas distribution and kinematics and constructing the corresponding mock data cube. KineMES is then coupled with an MCMC code which feeds the data and then outputs the full Bayesian posterior probability distribution. And if you want to know more, I invite you to have a look at the Davis et al. 2013. So we carried out the kinematic study using KineMES, and in particular, since what we want to do is to model the gas kinematics in order to obtain the supermassive black hole mass, the most important thing is to accurately reproduce the gas velocity profile. And to do that, what we do is starting from the assumption that both stars and supermassive black hole contribute to the central gas kinematics. The next step is to construct a mass model for the luminous component to predict the gas circular velocity, assuming that the gas circular velocity is proportional to the mass to light ratio. And to do that, we carry out usually a multi-Gaussian expansion, an MG modeling. Once we have the contribution, the gas kinematics due to the stellar contribution, we remove this contribution in order to calculate the mass of the supermassive black hole, giving rise to the residual observed kinematics. Doing that, this is the result that we obtain. So on the left-hand side, you can see the PVD that I just showed. On the right-hand side is the same PVD with the best fitting model overlaid. And as you can see, adopting this approach, we are able to perfectly reproduce the observed gas kinematics, obtaining a best-fitting supermassive black hole mass of the order of 10 to the 8 solar masses, with very high accuracy, as you can see from the 1 sigma uncertainties quoted there. Just to give you an idea, as a double check, what we do also, what I show here is the same PVD with 3 different models overlay. So at the center is the model I just showed with the best fitting supermassive black hole mass. On the left hand side, you can see a model overlaid without the presence of a black hole, and you can clearly see that it's not reproducing the central structures, the central kinematics. And on the right hand side, another model with a black hole mass, an overly massive black hole mass. And again, from this plot, it is clear that the only model perfectly reproducing the observed gas kinematics is the best fitting one. The one with a black hole mass of 1 times 10 to the 8 solar masses. Now, the second object I'm going to show you today is the 4261. This is a famous giant elliptical, nearby elliptical galaxy, the BCG of a group in a pair with 4264. This is an alien. In particular, it's an FR1 radio galaxy, and if we look at this in the radio, it will look like this. So there is an extended jet component, which is mostly, well, essentially perpendicular to the central dust component. 4261 is among the high mass supermassive black hole mass candidates, and it is famous also because it was one of the first ones studied by Ferrarese, who obtained a black hole mass measurement through ionized gas kinematics of the order of 5 10 to the 8 solar masses. 5 times 10 to the 8 solar masses. Again, an ALMA dataset, CO21 dataset consisting on 3 different array configurations was available for this object. Combining the data, we obtained a dataset with a final spatial resolution of the order of 40 parsec in this case. Again, here I show the moment maps and position velocity diagram of the detection. As you can see here, we detect again a rotating CO disk extending again on the central 200 parsecs. So this disk is typically very concentrated at the center of the galaxy. But in particular, the thing I want to highlight here is that if we look at the position velocity diagram, we can see that it's completely different with respect to the previous one. In particular, there is a sign of a circular velocity component, but the dominant one is this abrupt velocity increase at the center, which is likely related to the presence of a high mass supermassive black hole at the center. Again, we carried out the kinematic modeling in the same way I just explained a few minutes ago. And as you can see also in this case, from the plot on the right-hand side, we are able to obtain a reliable, best-fitting kinematic modeling reproducing most of the features we observe in the gas velocity curve, and in particular obtain the best-fitting supermassive black hole mass of the order of the 10 to the 9.21 solar masses. Just to give you an idea, again, I'm going to show you a comparison between different overlaid models. And here it is nice to see, in particular, on the left-hand side, we overplot a model without a supermassive black hole. And you can see that in this case, the kinematic component related to the presence of a supermassive black hole is dominant, is clearly dominant. Because if we don't include the supermassive black hole, we are basically not able to reproduce anything in the gas kinematics. Whereas in this panel on the right-hand side, we overlaid the model in which we basically set to 0 the contribution of stars. And in this case, you can see that basically the kinematics, the reproduced kinematics, is essentially the same as the plot in the middle, which is the best fitting one. So what it's telling us, this plot, is that the contribution of the supermassive black hole in the kinematics of the gas is dominant, whereas that of the stars in this case is not. And in particular, one thing that I would like to highlight is that the mass we obtained from CO dynamical modeling, which is again of very high accuracy, as you can see from the 1 sigma uncertainties quoted there, is about 3 times larger than that obtained from ionized gas kinematics, and is also consistent with another CO dynamical measurement carried out by other authors using a different modeling technique. So this is also useful for cross-check studies between different techniques that are now going to be adopted for this kind of studies. Wrapping up things before concluding, I would like to show you this plot, the M sigma plot, in which I overplotted the measurements of 1574 and 4261 that I just described. And in this plot in particular, there are the literature measurements in gray, the CO dynamical measurements obtained so far are plotted in red, and in blue I show 1574 and 4261. Now, as you can see, all the measurements are consistent, are within the scatter of the relation. Most of the CO dynamical measurements cluster around the best fitting relation, and 1574 is at the outer lower edge of the relation, but considering the error on the sigma, on the velocity, the central stellar velocity dispersion, it is possible. I mean, we cannot draw a solid conclusion on this position, whereas 4261 lies towards the upper edge of the scatter. And one thing that I would like to highlight from this plot is that 4261, which is a radio galaxy, similar to ours, cluster at the outer edge of the relation. And this is typical. This is typical of active galaxies. So galaxies with active supermassive black hole at the center. Of course, we need to keep on studying this kind of this relation, to carry out this kind of studies to draw solid conclusions. But I just wanted to highlight this particular point. And yeah, that's it. I leave you here with my conclusions, and I will take any questions.